0.5, I guess, right? So homework 0.5. Unless there were any other questions from the first one that we didn't get to, but I think we went through most things.
Can we go over number 7?
Number 7, yes. Do you have that? Number 7? Number 7 says, and this is from the very first one, right? Oh, good question. Yes, this is one we should look at. F of x equals 1 over x squared minus 9, and you're asked to find, and my guess is, not too much trouble with this one. Maybe this is weird, and maybe this is where all the trouble is. Does that sound accurate? Okay. So let's look at, so typically what this is, I like to think of this in a slightly different way, and maybe this is helpful to you, maybe it's not. I think of it as, all right, so the x is just a placeholder, and whatever, and the parentheses work in my brain better, right? So part of what I think you're doing in your first semester, not everybody's in their first semester here, but a lot of us are, is trying to figure out how we learn best, right? Some of us are very visual learners, and I told you I'm a very visual learner. I have to, in fact, if someone tells me something, I'll almost surely forget it. So if you're going to ask me to do something, like, can you be there at 3 o'clock, you see me at lunch, you better email me. Because if it goes in my ear holes, it doesn't guarantee that I'll remember anything. I'm a very, very visual learner. Some people are more auditory learners. Some people are, I think we're all a little bit of everything. But I always have to do something visual for myself to make it work. And so for me, this doesn't quite work. This does it better for me. Right? So basically it says this function f depends on whatever's inside here. And whatever I put in here, I've got to first put it in the denominator with 1 on the top, square it, and then subtract 9. Most people don't have problems with the numbers. So, for instance, f of 0, I plug in 0, I do the calculations, and I get 1 over minus 9. Is that what everybody got? Mm-hmm. All right. F of minus 3, I plug it in, I do the minus 3, I square, I get a 0 in the denominator.
Undefined.
And so I say f is not defined. Most of us may have noticed that beforehand. And then finally, f of x plus h. And this particular composition is one that we'll do a lot in here. All right? There'll be you're not going to like it, but we have to do it a lot. And so for f of x plus h, everywhere I have these parentheses, see the parentheses are there now, and you're less likely to make this mistake where you don't know where to put it. Whatever I put in here, I put in here. If I put Bill in here, I put Bill squared down here, right? X plus h here, x plus h goes down there. Now, I don't remember what the answer looks like, but you can stop right there for right now.
The answer's like this.
And so the answer is I don't know what they did. Because you have no reason to do this. It's simplified. I imagine they could have multiplied that out. But at this point, there's no value, there's no reason to do any more than this. And I don't want anything we do in this class to seem like mindless manipulation. Tedious stuff that someone made you do because they said do it. Right? This is bad enough. But there is a reason we need this. And so when we develop a thing called the derivative, I need to talk about a function with x plus h plugged in. So I want to make sure we can feel comfortable doing that. And I want to stay away from as much as possible, believe me, you're going to need it. Because you've heard 12 years of believe me, you're going to need it. And you maybe haven't needed it yet, right? So, and this is the best way to think of it, no matter how complicated it is. Now, whatever goes in this parenthesis goes in there, and I just do whatever it says. Does that help? And then it's like easy, holy crap. I mean, I remember when I came up with this in my own head somewhere in college. It's like, man, I struggled with this for a while. Now this makes it very easy. Now, just because it works for you, for me, doesn't mean it'll work for you.
So on the x plus h, we just leave it at that? Or?
That's fine.
Okay.
We're gonna when we develop it later on, we're going to need to do some simplification. But what we're going to have to do is we're going to do something so we can work with it. All right? And you'll be motivated to do something Because what you'll do, you'll plug some stuff in, you'll get 0 over 0. And you're like, well, I don't know what to do with that, all right? Like, something over 0 I know is undefined. 0 over 0, we're not quite sure what's going on yet, all right? Other questions about this problem? All right, what about questions from the next homework assignment, from point 5? Yes, ma'am?
3 and 5.
3 and 5. See that? Yes. 3, 5, and 4. Anybody want to do 1 and 2? Just do them all? Okay. So let me talk a little bit about this. This section, although short, is the type of algebra we'll use more frequently in this class than any other type of algebra. All right? We'll be finding out where things are positive and negative more than anything else. And the reason why is, remember what I talked about the other day. Our goal in this course is to decide what functions look like, right? We want to be able to sketch the graph of functions so we can decide what they're going to be doing. You know, how high they go, how low they go, are they always positive, are they always negative? How often do they cross the x-axis? All those things are important. So, to know where, let's just say we have f of x, this function. Notice, if I know where f of x is equal to 0, and I'm trying to sketch this graph, right? And let's say this happens at x equals plus or minus 3 and 4. Right? Let's just say that happens. We don't have an answer yet. We don't know what f of x is. But let's say this version, this function, I could write one. X is 0, plus or minus 3 and 4. That means over here at minus 3, the graph crosses the x-axis. I have an x-intercept. Over here at 3, I have an x-intercept. And 4, I have an x-intercept. And there's a whole bunch of things that can happen in between. The graph could go up and come back down and go back up. The graph could go up, come down, just touch, go up, come back down. I mean, right? So if I now knew where f was positive and where f was negative, I'd be able to have a pretty good picture of what the sketch of the graph looks like without doing any calculus at all. In fact, if you were taught algebra correctly, this is what you did to sketch graphs. And my guess is maybe many of you have seen this version. So the question is, how do I decide where a function is positive or negative? And unfortunately, in Algebra 1, they typically start telling you this bullshit version, I can't think of a better way to say it, bullshit version of solving inequalities. And they want to be able to model it exactly from solving regular equations. So they give you something like that first problem. I don't remember what it was, but they're all the same. Right? And here, what you get is, well, you play the same rules, right? I add a minus 2 to both sides. And then I'm allowed to multiply both sides by anything I want, or divide, however you like to think about it, as long as it's positive. If it's positive, it doesn't change the inequality, right? And if it's negative, it flops the inequality. Why? Well, I think maybe some of us understand why, and maybe others will say, I don't care why, I know it does it. Right? But I want to understand a little bit more than that, and so I get x is greater than or equal to 2/3. Now, I change this to something like 3x squared plus 2x is greater than or equal to 4. And now all bets are off. I no longer know how to solve this inequality. You can start trying to move things to both sides. I don't know rules about taking square roots on both sides. Because sometimes when you take the square root of something, it gets smaller. 9. You take the square root, it gets smaller. And sometimes you take the square root, it gets bigger. Take the square root of 1/4, it's 1/2. So now those rules don't work. So then they give you a whole different technique. But I'm going to show you in general this nice way to do it, where you do every problem exactly the same way. And it's based on a visual interpretation of the graph. So, for instance, first let me say I've got this function, y equals f of x. And I want it to be continuous, all right? Because everything is nice if it's continuous. And does everybody, what's the definition that you used for continuity in high school? Does anybody remember?
You don't pick up your...
Ah, perfect, right, so this is the one. You can sketch the graph without picking up your pencil, right? Has everybody heard that? Okay, so that means, now, as long as that's true, and with polynomials and the things we're going to be working with, it is almost always true with polynomials, all right? And most nice things, it's true. And we can get around the things that aren't the bad things, like we have 1 over x squared minus 9, we had that. We can get around that by doing something different where it is continuous. And I'll show you that. Now, let me just put some numbers in here. Minus 3, and 3, and 4. And I can ask you now, where is f greater than 0? Okay, surely after the 4.
Between negative
And between negative 3 and 3. And typically the way you would have written this back in high school possibly is something like this. F of x is greater than 0 from minus 3 to 3, union 4 to infinity. Does that sound familiar? Okay. And f is less than 0.
Negative infinity.
Negative infinity to minus 3. And 3 to 4. Right? Okay. For me, as a visual learner, and trying to interpret what a function looks like and what the picture looks like, this doesn't help me. I don't think in intervals like this. And I don't think in unions. Now, if you do, by all means, use this technique. You know, writing it down like this. I like to say this, and this is the way I'll take the answer. So I might say, find where f is positive and where f is negative. The x's indicate x-intercepts. It's where it crosses the x-axis. This tells me where the function is negative and where the function is positive. Below the axis here, above the axis here, below the axis here, above the axis forever after. Now, if I had to sketch this graph, I can make this my x-axis, just right above it. And now I can simply go. It looks something like this. I think we call these, I heard these things called wiggle graphs. Right? Because you don't know what the hell happens up here. This might do some crazy shit like this and then come back down. Right? But you don't know. So you get a basic idea. And the calculus will allow us to know if this happens or not. But right now we're not doing any calculus. So our goal is to use that rule. And here's the interesting thing. Look. Once it's positive, it's always positive. And the only way it can go negative is by crossing the x-axis, as long as the function's continuous. Does everybody see that? So if I know the function's continuous, and I find all the zeros everywhere it crosses the x-axis, all the x-intercepts, those are all the same thing. Right? The zeros of a function, the x-intercepts of a function, where that function crosses the x-axis, where the graph of that function crosses. Those are all the same thing. Once I know that, now I know that in between those regions, the function is always positive or always negative. So all I need to do is do just one checkpoint. All right? Let's do a simple example. So, the thing is, the way I'm going to do the problem is we're going to answer the questions much, much more carefully than they even ask us to. So if I say, find where x squared is greater than 9. Now, this is a simple one. All right, I'm going to do a simple one. We don't want to see that. We're going to put 0 on one side always. All right? So I'm going to get everything over to the one side if it's an inequality. So my question is, where is x squared minus 9 greater than 0? Now I'm talking about where is this function, y equals x squared minus 9, above the x-axis? I've now turned it into something physical for me to think about. And I'm going to answer both questions. Where is it positive? Where is it negative? And the third question, where is it equal to 0? So the first thing we do is find where x squared minus 9 equals 0. So first. Hey, see, we're good at this. Has nothing to do with inequalities. No extra rules to remember because we're just doing we have enough rules in solving equations. And this is one that you can either, what I said, called extract square roots or factor. I think most people like to extract square roots, so we will. So we say x squared equals 9, or x equals plus or minus 3, right? So I took the square root of both sides and then took all possible numbers that when you square, you get 9. And I put them on the number line. Yes, sir?
Are these the same thing as like cut points? Is that what they call them sometimes? That line, the number line right there?
They could be. That sounds like, I've never heard that.
You just plug like any random number and it's...
Yes.
Okay.
And then they were called, I can see they would call them cut points because it's where it crosses the x-axis.
Right.
So we get them at plus or minus 3. I put x here because if I was graphing the function y equals x squared minus 9, it would be an x-intercept. And occasionally, we're going to see some places where it changes sign. It's not an x-intercept, it's a vertical asymptote. We're going to do those differently. We're going to put dotted lines. All right? We're just going to call them zeros in the denominator right now because we don't know what the hell a vertical asymptote is yet. We don't have a definition, but we'll get it. All right. Now, with this thing that we know, the polynomials are always these nice continuous functions. These are the only places it can cross from positive to negative. In this region, it's either always above the axis or always below the axis. And if it changed somewhere over here, it would have had to cross the axis again. But I don't have any more crossings over here. So I take what we call a test point. Any point in this region, minus 4, works nicely. Anything in the middle here, same thing. It's either always above the axis or always below the axis. 0 works nicely here. And then over here, it's always above or below. I don't know which one. You're not supposed to know which one yet. I mean, maybe we all know what this looks like. We know the answer, but 4. Now I take this and I plug it in. I plug minus 4 into the original expression that I'm trying to see where is it positive and where is it negative. I plug in minus 4, squared is 16. 16 minus 9, positive. That means that function is always positive in that region. And it doesn't matter which number I picked over there, because it's always positive, otherwise it would have crossed the axis again, and it hasn't. Pick something in here, we pick 0. 0 squared is 0, minus 9 negative. Means the graph is always below the axis. Yes?
I was just wondering, 'cause if it's a square, then can you automatically assume that the opposite side is also positive?
Yeah.
Right.
What if it was like minus?
Yeah, I mean, it could, it could go down and touch and come back up. So you might only have 1 0 there, right?
Yeah.
It's like x minus 1 quantity squared kind of.
Okay.
So there are times with a square, if it goes plus minus, the next one's going to be plus. If it went minus plus, the next one will be minus. If it's quadratic. But in general, it doesn't go plus minus plus minus plus
Yeah.
minus. It doesn't have to. Plug in 4, I get the same thing, 16 minus 9. And it's because if you plug in the same thing, right, the square doesn't matter. You're going to get the same result.
Yeah.
Positive. And so I even go so far as to say above the axis, below the axis, above the axis. You don't need to do that. But it just helps me. So now, I've answered this question. Where is it greater than 9? Well, it's where this is greater than 0. And where is that greater than 0? From minus infinity to minus 3. And 3 to infinity. The nice thing is, if you draw it for me like this, you've answered even more. You told me where it's equal to 0, and you told me where it's negative. So you can just write this for this answer. Nothing else. If you really hate the picture, don't use it. Then write this, if this is what you really like. If this makes more sense to you. But to me, that doesn't. And to most students, it doesn't. Like I said, most of us are very visual learners. So if you can attach a picture to it, it makes things better, I think.
Use for union and
Yeah, use for union means stick it together. And the upside down one's intersection. It means the things that are common. But we can just do this and never even deal with that notation. And the reason why is we're going to end up doing number lines like this for 3 different functions that are related. Okay? And then we're going to take that information and turn it into a picture. And so when you have all the information visual, to create a visual picture, it's just easier than to go from a notation that looks like this. This is the way the way people teach it. In fact, I don't know anyone else that teaches it like this except people here who saw me teach it, and they like it better. And because the table with the unions and stuff in it, just a table of intervals, it doesn't translate to a picture easy as that. Right? When I draw this picture, above the axis, below the axis, above the axis, done. I mean, it almost tells you exactly how to draw it. It doesn't tell me how low, although we know how to do it for quadratics. Once we get to a cubic, we don't know. We know how low it goes here. All right? So, let's see how it works on that first problem. Let's just do number 1. And what is number 1?
X minus 7 is greater or equal to 8.
X minus 7.
Of 3x
3x
minus.
minus 7 is greater than or equal to 8.
All right. So, never have an 8 on the one side. See, and here's the nice thing about this technique. I don't have 2 different techniques. Oh, if it's linear, do this. If it's non-linear, do something else. I simply add a minus 8 to both sides to get 3x minus 15 is greater than or equal to 0. Right? Find the x-intercepts. Find where 3x minus 15 is equal to 0. Add 15 to both sides and divide by 3. And plot it on a number line. Sorry, that was louder than I meant to be. Plot it on a number line. Put an X on it. It's an x-intercept. Get all this information from this one picture. Now, check to the left. Plug in 0. 3 times 0 is 0 minus 15, it's negative. Plug in 6. 3 times 6 is 18. Minus 15 is 3 positive. Actually, I don't even care what the number is, just if it's positive or negative. And now I know whatever this graph looks like. Right, I even know it's a line. And we expected it to be from negative to positive. We're expecting a positive slope. Right? So it slants upwards from left to right. All right? So now we have this nice technique that will always work. So the next one was, let's try number 3. 3 says x minus 3 over x minus 2 is what? Like that. Or equal. Yes.
So there's a problem with your road board right here, so.
Oh, that one, we haven't done that yet. We'll look at that one. That one may be uglier than we care to do. Because I just wrote it down. So he's talking about the quadratic 3x squared plus 2x greater than or equal to 4. If it doesn't factor, then you got to use a quadratic formula. And you can do it, and then your numbers are going to be 1 plus or minus the square root of 7 over 9. You know. So I was just using an example that the old technique doesn't work. Now this technique is interesting in the sense, this problem is it doesn't seem to fill the rule that I said it had to be continuous. Right? This has a problem where x is equal to 2. You're going to 0 in the denominator. That's not an x-intercept. But the nice thing about it is that it has exactly the same positive or negativeness above or below the axis as a product. So here's what I'm saying. Say f is continuous and g is continuous, right? Nice, smooth functions. F times g is also continuous. So f has, let's just do it this way. F and g, right? Let me think that's the best way to do it. Maybe this way. F and g. Positive and positive, positive and negative, negative and positive, right? And negative and negative. Okay. This is all possibilities, right? So f times g, what's the result? If f is positive, g is positive, the result of the product is? Positive. If one's positive and the other one's negative, the result is?
Negative.
Both are negative. If one's negative and the other one's negative, the result is? What about f over g?
Exact same.
Same exact thing. So our technique will still work. Instead of finding out where this is less than or equal to 0, right? Less than or equal to 0. We'll do the same thing. Right? The only problem is I don't have an x-intercept. X can't be 2, right? X can't be 2 here. So we'll indicate that on our picture. So here's the way we'll do it. We'll either find out where each term is 0, or where the top is 0, or where the bottom is 0. It's the same thing. The difference is, when the bottom's 0, I can't put an X on my number line. I've got to put something else to indicate it's not an x-intercept. It's a problem point. Right? So, here we go. Where's the top equal to 0?
3.
Top's equal to 0 with x minus 3 equals 0, or x equals 3. Where's the bottom 0? Right? That's where x minus 2 equals 0, or where x equals 2. X equals 3 gets an x. X equal 2. I put a dotted line through. You don't know what that means yet. There's a reason we choose dotted lines. I know you've all seen vertical asymptotes. That's why we're doing it this way. And now, I'll put it here. I plug in a 0, and what do you want here? 2.5, and something over here like 5. It doesn't matter. Now plug in. Plug in a 0 here. 0 minus 3 is negative. 0 minus 2 is negative. Negative over negative is? Positive. Positive in this region. Whatever this graph looks like, it's always positive to the left of the vertical asymptote. Plug in 2.5. 2.5 minus 3, still negative. 2.5 minus 2, positive. Negative over positive, negative in this region. And finally, plug in 5. 5 minus 3, positive. 5 minus 2, positive. Positive divided by positive, positive. There's everything you need to know about that graph. It answers this question. It tells me where it's less than or equal to 0. It is less than 0 from 2 to 3. Not inclusive. Don't include the endpoints. It's 0 at 3. And it's positive when you're greater than 3 or less than 2. So that picture answers this question and then every other question that you might ask about above or below the axis. Now, to sketch a rough graph of this, we need to know what vertical and horizontal, what a vertical asymptote does and what a horizontal asymptote does. But the calculus, once we get our definition of those things, will help us.
Yeah, so 3 is the x-intercept?
Still an x-intercept.
2 is the what?
2 is what we call a bad point at this point. It's 0 in the denominator is bad. Yes, ma'am?
I think you don't need always thinking about the positive or negative about this, because the x equal, if it's positive, it's always like this, right?
Okay, so if x is positive,
Yeah, it's always, can I show you?
yeah, sure.
if like this, x equal, the picture will be always like this. If it's negative, the picture will be always like this. So you don't need to think about this. So just check the equal here, whether it's negative or positive.
So if it opens up, right, but I want to introduce a technique, that this technique will work no matter what. So I'm doing a technique on a simple problem first, right? So she's absolutely right. If it's quadratic, it is either a U that opens upwards or a U that opens downwards. But it could be all above the axis and everything could be positive, but there'll be no zeros.
I mean, if your picture will be better than the negative or positive.
But in general, this technique, so how would you handle something like this then?
I just thinking about the equal.
About the quadratic, right? Yes. So I'm doing a simple problem that we use a technique that does here. My guess is most of us won't have to do anything more complicated, but I just want to introduce the idea of how we do it on simple problems first. All right? So that was 3?
Mm-hmm.
What's 4 look like? X squared plus 1 over x squared minus 9. X squared plus 1 over x squared minus 9. And this is less than 0. All right? So the same idea occurs. We're going to find where the top is 0, the bottom 0. This is now x squared plus 1 times x squared minus 9. You're thinking of it as almost a 4th degree polynomial. Could have as many as 4 different places where it changes the sign. Yes?
Before you get too far into on this one, can you explain why you didn't include that endpoint on there? Because in the last one, number 3, sorry,
Yes.
I erased it. It was greater than or equal to sign. So why didn't you include the endpoint on 3? Yeah. Because it's greater than or equal to.
It was like this?
Or less than or equal to.
Right. Is this the way it was?
Yeah.
Yes. Okay. So it's included by putting an X there.
So that would be included if you did like with a union, you could do a bracket instead of a.
Right, that's right. So if I wrote this answer out, if I was looking where it was less than or equal to 0, right? I can't remember, was it less than or greater
Yeah,
than?
less than.
Then you would say 2 to 3, like that,
Okay. All
right?
Okay.
So you would include it. In my picture, the way we draw, the way you figure out where the zeros are, you look at the X's. And I don't think about an interval together with an endpoint or not with an endpoint. Okay, but that's the way you would show this answer if you're using the interval notation.
Thanks.
Other questions about that? This one, I still do the same technique. Find where the top is 0, find where the bottom is 0. Top is 0. And if you don't notice right away that this is never 0, right? Because x squared is always positive. I add 1 to it, it's even more positive. It ain't never going to be 0. If you think that way, you're done. Or it may take you one more step. When you see a squared is equal to a negative, you will hopefully automatically say, this doesn't happen. There are no x-intercepts. This never crosses the axis. That top is always positive. All right? Bottom 0. We already did this problem, didn't we? X squared minus 9 equals 0 at x equals plus or minus 3. We just did that problem. It was my example that I did. All right? So
that means it's always positive, but at the -3 and +3, there's bad points.
there's bad points here. Well, what it says is it's exactly positive and negative where the bottom is positive and negative. The top doesn't change anything because the top's always positive. The nice thing is, if you don't notice that, it doesn't matter. Once you see that there's no zeros, and you plug in a -4, a 0, a 4, this answer is going to look exactly like the x squared minus 9 answer, right? It's going to be a u. Although the graph is going to look much, much different than a u. It's much more interesting. So let's see what happens. I plug in and now I'm plugging into x squared plus 1 over x squared minus 9. I plug in a minus 4, it's positive. I notice the top is always positive, but it's 16 plus 1, it's positive. The bottom is 16 minus 9, it's positive. Positive over positive is positive. Plug in 0, top is still positive, bottom is negative. Top is, plug in 4, the top is still positive. Notice it's always positive, but it didn't matter. It took us an extra 2 seconds to plug it in if you didn't notice that. And you get the bottom is positive, so this is positive. So this graph looks very different from the quadratic x squared minus 9, but its number line looks exactly the same.
Would the graph itself be like the U up and then down?
The graph itself will look something like this.
Yeah.
It won't cross, it doesn't touch the axis.
Yeah.
It's 0, because at 0 it goes almost up. It goes up to minus 1/9. Just barely, but doesn't touch the x-axis. But we don't know that yet.
So if you were to write that with the union, how would you write it?
This answer is minus 3 to 3 open on both sides.
Yeah.
That's where it's less than. Right? But you can leave the answer just like this. So when I say find this, you show me this. You've done more work. You show me where it's positive and where it's negative. Okay? Or give me that if that's the way you want to do it. And how about number 5? X to the 5th, let me write it down, I'll never remember that. X to the 5th minus 3 greater than x to the 4th minus 3. Okay. So as I say, we don't want to deal with anything on the other side but 0, because I'm talking about functions being above and below the axis. And we know the one rule for inequalities is I can add anything I want to both sides. Right? Positive or negative, it doesn't matter. So I subtract this, I get x to the 5th minus x to the 4th minus 3 plus 3 becomes 0, greater than 0. So this is the example that I said, what happens here? Now this is not a quadratic anymore. It's not a nice function, as nice a function as a quadratic. So we try to find where that's equal to 0. Yes, sir?
Can you take an x to the 4th?
So in order to find where this is equal to 0, we're going to factor, exactly. So x to the 5th minus x to the 4th equals 0. It's critical that you don't divide by an x to the 4th, because you can lose a solution that way. Factor an x to the 4th out front. Yes? And now I use that 0 property. That means either x to the 4th is 0 or x minus 1 is 0. If x to the 4th is 0, then what do you know about x? It must be 0. And if x minus 1 is 0, then x must equal 1. Those are both x-intercepts. There's no denominator here. So there's no problem. There's no vertical asymptotes or holes. So I plug in, I put up a 0, I put up a 1, and now I've got to plug in some nice points like a minus 1, a 2, and something in here like a half. All right? I like to think of the factored version. It makes my life a little bit easier, but you can use any version you want. Because when I say x to the 4th here, what do I know about that? Always positive. I don't have to do any work there. But if you don't notice that, you plug something in. It's fine.
So on your drawing, the number line, the 0 and the 1 would have to be...
Yes, they have x's. Thank you. So now I plug in minus 1. This is still positive. Plug in minus 1 here. Minus 1 is minus 2, which is negative, and that's negative. Now I plug in a half. 1/2 to the 4th power is positive. 1/2 minus 1. Negative. Here's an example where it doesn't go negative, positive, negative. Right? And I'll show you what special thing has happened. Now I plug into positive, that's positive, this is positive. So whatever this graph looks like, It's negative, it comes up, it touches the axis, stays negative, and then comes back up. It doesn't go very far down, by the way. And it turns out to be not this vertex, this what relative min, as we like to call it, this valley, does not occur at 1/2. You know, like the vertex of parabolas are always right in the middle of their zeros. This does not. It's way over here somewhere. Maybe 4/5 or something. Yes.
What? Can't you just do that problem without doing any math though? If you know the properties of the powers.
Okay, tell me what you would do.
Like, so you'd see like x to the 5th is an odd power.
Yep.
So anything below 0 is going to be low.
Negative.
Negative.
Yeah.
And then x to the 4th is going to be positive. So it'll be negative because it's positive and negative. And then everything between 0 and 1 is a fraction. So it'll be negative.
Oh, yeah, yes, you could probably figure it out that way. Yes.
So that's what I said.
That's no problem doing that. You can absolutely just say, oh, if everything's negative, this will be negative and bigger, right?
I mean, it just, the equation ends up being x to the 5th is greater than x to the 4th. If you do the math.
Not always.
No, I mean, if you were to do it the way that you were taught.
But this is not true. X to the 5th is not always greater than x to the 4th.
I know, but if you look at it like a.
If x equals 1/2, it is. And well, let me tell you this. My technique is, if you don't like it, use something else. Okay? My technique will always work. I'm not sure that yours will.
Yeah, I mean, like, understand.
Right? Your technique, the more complicated the problem is, the less likely you're going to have insight into what the problem will do. This, as long as you can factor it, you can do it. This will always work, as long as you can find the zeros. My guess is, in general, any kind of insight you might have might not exactly be what you need to do. Yes?
So in interval notation, it would be, the answer to this would be 2 to infinity, the bracket on 2. Or 1 to infinity.
1 to infinity, and it's strictly greater. Was it strictly greater?
Yeah.
So no brackets. So just like this?
Oh, yeah.
Okay. And there will be some that are obvious. What I need you to do, though, is give me your answer any way you want. I'm going to suggest strongly that you give me the answer this way, because there will be a time that you have to do this. I will say draw number lines for this, because you're going to have number lines for f, f prime, and f double prime, and they all mean different things. All right. However you fill out the positive and negativeness, I don't care. You have a crystal ball, fantastic. Actually, no crystal balls in the Turing test.
Are we going to have a quiz next time before we go over the next section?
We're very likely to have a quiz on Friday where I'll say, take out, just write down the answer to number 7, number 4, whatever. All right. So what we'll do, we'll finish. We won't actually get in. Let me get 15 minutes of my review of trigonometry, because that's the only section left. Is that right? Mm-hmm. And then Friday we'll review trig. Now let me tell you this. In general, for reviews, say you don't need any reviews for trigonometry. You know how to do all these problems. Don't come Friday. All right? You don't have to come on a review day. Homework days you have to come on, but on a review day, and I'll call this a full-blown review day.
So Friday is review.
We're going to review the trig material. If you already think you know the trigonometry well enough, you need not come to class. Shit, I just said we're going to have a quiz then, right? All right, we'll do the quiz on Monday. So we won't do the quiz on Friday. All right, so here's the idea that I want to talk about, because you've seen these things. Cosine theta, sine theta, tangent theta, right? All these things. And I want to talk about what they are. We will almost exclusively use radians in this class. Some of the homework is translating from radians to degrees and back and forth. but in this class, you want a real number. Radians are unitless. I'll explain what a radian is, physically what a radian is. But what I want to know first is the following. So if you take any length rod and you spin it a certain, right, and you spin it around, I think everybody knows if you take a string, nail it to the center, I don't care the length of the string, put a pencil in and spin it around in the circle, spin it around, you'll draw a circle. All right? And if this happens to be unit length, it'll draw out a circle of radius 1. So if your line is... Now I want to know, there is, if I measure this angle, so you have a protractor, everybody remember what those look like? Do they still use those in high school? Okay, so a thing to measure an angle, if not, you have some kind of way to measure that angle. There is a nice correspondence, and I'm just going to talk between 0 and 2 pi, or 0 and 360 degrees, just there. There is a one-to-one correspondence between an angle and a point on this circle. Right? There is some function here. There's some, I'll call it x of theta, some formula that gives us the x-coordinate, and there's some formula. You know, so maybe it's something like theta squared minus 3 theta plus theta minus 8. That's not it, but you know, it's some formula. Does anybody know that formula? That will, if you tell me the theta, for instance, it will tell, I plug in theta, it will tell me exactly the x-coordinate that it points to. Huh?
Just the Pythagorean theorem.
Is it the?
You know the sides, but we don't know any of the sides here. All I know is this angle.
Is it like hypotenuse?
There's some formulas about sine and cosine using those, but this is, I just want to know, does everybody agree that there's probably is a formula?
Yes.
Mhm.
I agree.
That is, that if you took a piece of stick and you rotated it up and shined the light down, you could come in here and measure it, the shadow, and that would tell you the x-coordinate.
Sure.
Okay? But in the formula, is there a formula that involves just theta?
No.
There's not. There's no known formula that tells that. So what we do is, when I want to talk about that in mathematics, instead of saying, you know, the point on the circle where you rotate the stick by theta degrees and you get the x-coordinate, you don't say that. You say the cosine. X is the cosine theta. There is no formula. When you plug it in your calculator and you do 29 degrees and you hit cosine of 29 degrees, it doesn't know the answer. It gives you an approximation. The approximation different calculators use is proprietary. TI, which is the most common, I know something about that technique. If you go into Calc 3, you'll learn other techniques. It's a guess. There's a handful of ones that we know exactly, and the rest are a guess. Okay? We have nice ways to calculate it, get very close to it, but there is no formula. And the Y one is the sine thing. And that's it. We don't know it, but I want to be able to work with it because it allows me to do a lot of problems, particularly in physics, right? Because physicists, for some reason, are obsessed with sliding shit down a ramp. And they love doing this, and you need to figure out these forces, right? And this angle has something to do with it. And that sine and the cosine have something to do with it. And that's why you have to have a calculator to do this, except for a handful. And the handful of ones that we know, we're done, right?
Yeah.
I don't know why I looked up at 1:45. I thought we had 51 minutes. I don't know why that was, but we will finish this conversation on Friday. If you already know all this stuff and you feel like you would be bored senseless, feel free to not attend. And we'll do a quiz, the review quiz on Monday.
say we don't have to come up with the right